This is the lecture for section 4.6, Irreducibility in R bracket x and C bracket x. As seen in the last section, in general, it can be very difficult to determine whether or not a polynomial is irreducible in Q bracket x. The situation is very different, however, in R bracket x and C bracket x. In this section, we obtain complete characterizations of the irreducible polynomials in R bracket x and in C bracket x. We'll start with irreducibility in C bracket x. We have theorem 4.26, which is called the fundamental theorem of algebra. And this states that every non-constant polynomial in C bracket x has a root in C. So every non-constant polynomial with complex coefficients has a complex root. Now, a field with the property that every polynomial with coefficients in that field has a root in the field is said to be algebraically closed. So the fundamental theorem tells us that C, the complex field, is algebraically closed. This was first proved by Carl Friedrich Gauss in his PhD thesis in 1799. Now, all known proofs of the fundamental theorem rely upon results from analysis or complex analysis and are very complex, so the proof is omitted here. We can use the fundamental theorem, however, to characterize irreducible polynomials in C bracket x. We have corollary 427, which states that a polynomial in C bracket x is irreducible in C bracket x if and only if it has degree 1. So this is telling us that the only irreducible polynomials in C bracket x are the linear polynomials. To prove this, first note that we proved earlier that every first-degree polynomial is irreducible over any field, so the backward direction holds. To prove the forward direction, we'll use a proof by contrapositive. So suppose f of x is an arbitrary polynomial in C bracket x, and suppose f of x does not have degree 1, so has degree greater than 1. By the fundamental theorem, f of x has a root in C, so has a linear factor, and therefore f of x is reducible in C bracket x. And this proves the contrapositive statement, so proves the forward direction. Another corollary, 428, tells us that every non-constant polynomial f of x of degree n in C bracket x can be written in the form f of x is c times x minus a1, x minus a2, down to x minus a sub n, for some c, a1, a2, down to a sub n in C. This factorization is unique except for the order of the factors. To prove this, suppose f of x is an arbitrary polynomial of degree n in C bracket x, then theorem 414 implies that f of x can be written as the product of irreducible polynomials in C bracket x, and by the previous corollary, the irreducible polynomials in C bracket x are the linear polynomials. So f of x can be written as the product of linear polynomials. So f of x can be written as r1x plus s1 times r2x plus s2 down to r sub n x plus sn. Factoring out the leading coefficient in each factor, we obtain f of x is r1 times x plus s1 over r1, r2 times x plus s2 over r2, down to r sub n times x plus sn over rn. Finally, we can rewrite each of the factors, take out a minus, and so group all the r's to the front. We have r1, r2, down to r sub n, then x minus minus s1 over r1, x minus minus s2 over r2, on down to x minus minus sn over rn. And this has the form in the corollary statement, so the result holds. Now we'll look at irreducibility in R bracket x. So we want to obtain a characterization of the irreducible polynomials over the real field. We need to first review some basic properties of complex numbers. Recall that for any complex number c equal a plus bi, its conjugate is the complex number c bar, so a plus bi bar, which is equal to a minus bi. This is obtained by replacing I with negative I. For any two complex numbers c and d, it's straightforward to show that the conjugate c plus d, c plus d bar is equal to c bar plus d bar, and the conjugate cd bar is equal to c bar d bar. So this means that the conjugate of a sum equals the sum of the conjugates, and the conjugate of a product equals the product of the conjugates. Note also that c bar is equal to c if and only if c is a real number. So for our first result, we have lemma 429 for all polynomials f of x in R bracket x, and for all complex numbers a plus bi. If a plus bi is a root of f of x, then a minus bi is also a root of f of x. So if a polynomial with real coefficients has a complex root, then the complex conjugate is also a root. To prove this, we'll suppose f of x is a polynomial in R of x, and c equal a plus b sub I, which is in C, are both arbitrary. And suppose c is a root of f of x. We need to show that c bar is a root of f of x. So let's write out a formula for f of x. F of x is a sub n x to the n plus down to a sub 2 x squared plus a1x plus a0. Since c is a root of f of x, then f of c is 0, where f of c is obtained by substituting in for c. So f of c is a sub n c to the n plus down to a sub 2 c squared plus a1c plus a0. Taking conjugates in this equation, we obtain f of c bar is the expression, the entire expression with a bar over it. And we now know that the conjugate of a sum is the sum of the conjugates, so this will be a sub n c to the n bar plus down to a sub 2 c squared bar plus a1c bar plus a0 bar. And we know that the conjugate of a product is the product of the conjugates, so this will be a sub n bar c to the n bar plus down to a sub 2 bar c squared bar plus a1 bar c bar plus a0 bar. And again, using the fact that the conjugate of a product, in this case the powers, is equal to the product of the conjugate, or the power of the conjugates, this will be a sub n c bar to the n plus down to a sub 2 c bar squared plus a1 c bar plus a0. Now in this line, we've also used the fact that each of the coefficients of f of x is real, so the conjugate of each of the coefficients is just the coefficient itself. So a sub n bar is a sub n, a sub 2 bar is a sub 2, and so on. And so the expression on the right is now equal to f of c bar. Now since f of c is 0, then f of c bar, which we've now shown is f of c bar, is equal to 0 bar, which is just 0. So this tells us that c bar is a root of f of x, and this proves the corollary. We can now characterize the irreducible polynomials in R bracket x, and this is given in theorem 4.30. For any polynomial f of x in R bracket x, f of x is irreducible in R bracket x if and only if f of x is a first-degree polynomial, or a second-degree polynomial f of x equal ax squared plus bx plus c with discriminant b squared minus 4ac less than 0. For the proof, well, first off, the backward direction is left as an exercise. To prove the forward direction, we'll suppose that f of x in R bracket x is arbitrary. Suppose f of x is irreducible. We then need to show that either f of x is a linear polynomial or a quadratic polynomial with negative discriminant. So suppose f of x is not a linear polynomial. We then need to show that f of x is a quadratic polynomial with negative discriminant. Since f of x is not linear, then its degree is greater than or equal to 2, and by the fundamental theorem, f of x has a root w in C. Now lemma 4.29 implies that since f of x has real coefficients, that the complex conjugate w bar is also a root. Now since f of x is irreducible in R bracket x, then it cannot have any real roots, so both w and w bar must be complex non-real roots, so w bar is not equal to w. The factor theorem then implies x minus w and x minus w bar are both factors of f of x. So g of x equal x minus w times x minus w bar divides f of x in c bracket x. Now let's suppose that w is r plus si, where r and s are real numbers. Then w bar is r minus si, and g of x, which is x minus w bar, is x minus r plus si times x minus r minus si. And multiplying this out, we obtain x squared minus 2rx plus r squared plus s squared. And note that the coefficients of g of x are real numbers, so g of x is actually a polynomial in r bracket x. Now, since f of x and g of x are both in r bracket x, applying the division algorithm in r bracket x, there exists polynomials q of x and r of x in r bracket x, such that f of x is equal to g of x times q of x, our quotient, plus r of x, our remainder. And the remainder is either 0, or the degree of the remainder is strictly less than the degree of g of x. Now, since g of x divides f of x in c bracket x, then there exists a polynomial h of x in c bracket x such that f of x is equal to g of x times h of x, which we can write as g of x times h of x plus 0. This means that if we apply the division algorithm in c bracket x, the quotient is h of x and the remainder is 0. Now, since q of x and r of x are in r bracket x, then they also both belong to c bracket x. Since the quotient and remainder are unique, it follows that the quotient when we apply the division algorithm in r bracket x must be the same as the quotient and remainder when we apply the division algorithm in c bracket x. So this tells us that q of x must be equal to h of x and r of x must be 0. And we can then conclude that h of x, which is q of x, is actually in r bracket x. And since f of x is irreducible in r bracket x, then f of x equal g of x times h of x, where the degree of g of x is 2, implies that h of x must actually be a constant, d, in the real numbers. Then f of x is equal to d times g of x, which is d times x squared minus 2rx plus r squared plus s squared. So f of x has the form ax squared plus bx plus c for some a, b, c, and r, if you just multiply through by d and collect terms. Now, since f of x has no roots in r, its only roots must be complex and non-real. It then follows from the quadratic formula that its discriminant b squared minus 4ac is negative. Next up, we have corollary 431, which tells us that every polynomial f of x of odd degree in r bracket x has a root in r. To prove this, suppose f of x is an arbitrary polynomial in r bracket x with odd degree. We need to show that f of x has a real root. By theorem 414, f of x can be written as the product of irreducible polynomials. So f of x is equal to p1 of x times p2 of x down to p sub k of x for some irreducible polynomials p1 of x, p2 of x down to p sub k of x in r bracket x. By the theorem, each p sub I of x is either linear or quadratic, and by theorem 4.2, the degree of f of x will be the sum of the degrees of p1 of x plus p2 plus the degree of p2 of x plus down to the degree of p sub k of x. Since f of x has odd degree, then at least one of the p sub I of x has degree 1. Therefore, f of x has at least one linear factor in r bracket x, which means that f of x has at least one real root. Corollary 4.31 can also be proved using elementary calculus. If we suppose that f of x is an arbitrary polynomial in r bracket x with odd degree, since f then one of our two limits, the limit as x goes to minus infinity of f of x and the limit as x goes to plus infinity of f of x, must be minus infinity while the other is plus infinity. Since f of x is a polynomial, then it's continuous over the entire real line, So if the limit as x goes to minus infinity is, say, minus infinity, and the limit as x goes to infinity is plus infinity, then somewhere between the 2 points, or the 2 ends, the intermediate value theorem tells us that our graph must cross the x-axis, which means that it has a real 0. Now, even though the fundamental theorem tells us that every polynomial of degree n has n roots, counting multiplicity, the theorem provides no way of finding them. For a polynomial of degree 2, we have the quadratic formula for finding the roots. For polynomials of degree 3 or 4, formulas involving radicals for the roots, which were first discovered in the 16th century. Such polynomials are said to be solvable by radicals. To solve the general cubic polynomial, x cubed plus ax squared plus bx plus c equals 0, first substitute x equal y minus 1/3 a to reduce it to a polynomial equation of the form y cubed plus py plus q equals 0. Then the roots of this polynomial are given by y equal cube root of a minus p over cube root of a. 1 for each cube root of the quantity a is minus q over 2 plus the square root of q squared over 4 plus p cubed over 27. Now note that a in general will have complex cube roots. So a will have 3 complex cube roots, and that will give us 3 solutions for y. Now the general quartic polynomial can be solved by using a substitution to reduce it to a cubic and then applying the cubic formula. However, it can be shown that for polynomials of degree 5 or more, no such general formula for the roots exist. This was shown by Ruffini and Abel in the early 1800s and a little bit later by Galois. And this finishes off section 4.6, which finishes off chapter 4.